Okay, let's do some practice derivatives using all of our different derivative rules. So here I've got a product of a function, and I'm going to have to use chain rule. Remember, this is sine of stuff, not sine times stuff. Okay, so product rule, I've got two functions, function number one, function number two. Product rule says derivative of the first, so I got to take the derivative of this guy. The two just comes along for the ride. X to a power, the derivative is bring that power down and decrease the power by one. So I want 2/3 minus one. So maybe on the side, all right, 2/3 minus one would be 2/3 minus 3/3 negative 1/3. So that's my new exponent. So that's derivative of the first times, leave the second alone, sine of this stuff, plus, leave the first alone, times derivative of the second. I've got sine of stuff. The derivative of sine of anything is cosine of the same thing times the derivative of what's inside. This is chain rule because I've got a function inside a function. So now I need the derivative of this stuff. So the derivative of 3x squared would be 6x plus 0. I mean, I could write plus 0, but that would be silly. It's unnecessary. Derivative of 5, of course, is 0. Okay, so this guy's derivative is right there. For chain rule. Okay, so there's my answer. And maybe this could be cleaned up, maybe it couldn't, don't really care. Okay, here I've got a quotient rule problem. I've got two functions divided. And I'm going to have to use chain rule a couple of times in here. So y prime, which we might also call the derivative of y with respect to x, will be the derivative of the top. Okay, so I've got 3 times e raised to stuff. The 3 just comes along for the ride. The derivative of e raised to the anything is always e to that same thing times the derivative of what's up top. Chain rule, that's e raised to a function. So this guy's derivative is going to go here, and you should see that that's 15x squared. Plus this guy's derivative, plus 2. Okay, so if this is function number 1, this is number 1 prime here. Times the bottom, leave the bottom alone. This is quotient rule. So this is just number 2. Minus derivative of the bottom. So now I'm just looking at the bottom. The derivative of cosine of anything is negative sine, that same thing, times the derivative of whatever's inside. This is chain rule. I've got a function inside a function. The derivative of 5x is just 5. So that's that guy's derivative. I'm going to make this a little smaller. Okay, so that was derivative of the bottom. Oh, no, I'm not done. I still got this guy. So maybe we'll put some extra brackets here. Derivative of that guy would be minus 28x to the 6th. So all of this here is the bottom's derivative times the top, leave the top alone. All over the bottom squared. So I have to put the whole bottom in parentheses squared. And maybe this would clean up, maybe it won't. There will be times when we need to clean something like this up, but for right now, we're just taking a derivative and we'll leave it looking nasty like that. I don't care. Okay, here I've got a multiple chain rule. I've got a function inside. So I've got function inside a function, inside a function, inside a function. I'm gonna have to use chain rule multiple times. So S prime of t, which we might also call dSdt, because t is my independent variable here, will be my outsidest function is tangent. So that's the first one I look at. The derivative of tangent of anything is secant squared of that same thing. So leave the inside alone no matter what it looks like. To open one more. So secant squared of all that stuff times the derivative of what's inside. So now this guy's derivative will come over here. Derivative of sine of anything is cosine of the same thing. So I get a cosine of a cosine times the derivative of what's inside. So now I got to take this guy's derivative. Derivative of cosine of anything is negative sine of that same thing times the derivative of what's inside. So now derivative of this guy. And the derivative of 6t to the 9th would be 54 times 54t to the 8th. Now, you might think, oh, I can keep going. What about this guy's derivative? My insidest function now is just t. The derivative of t is just 1. If I try to go one more step, I would just get a 1. So we're done. Multiple chain rule problem. Okay, here I've got a log of a fraction. So I'm going to have to do chain rule because I've got a function inside a function. So g prime, which we might also call dg dx, because x is my independent variable. The derivative of natural log of anything is 1 over that thing. So I'll write it like this. Over 3x plus 6e to the x. Now, 1 over a fraction is really just flip the fraction over. So it probably would have been better if I'd just taken this fraction and flipped it over. But we'll leave it alone for now. Times the derivative of what's inside. So the derivative of all this stuff. This here is a fraction, so I'm going to have to use quotient rule. So this guy's derivative right there, his derivative is going to go here. And I have to use quotient rule because this is a fraction. So the derivative of the top would be 40x to the 7th plus 3. And I'm going to need parentheses all over the place here. Minus 0, derivative of 2 is 0. Times, leave the bottom alone. Minus derivative of the bottom. The derivative of 3x is 3. Plus the derivative of e to the x is just e to the x, and that 6 comes along for the ride. Times, leave the top alone. See, I got parentheses around all my different parts, all over the bottom squared. Now, this could definitely be cleaned up a bit, like this here. When I flip this fraction over, oh, I forgot my squared. One of these factors will cancel one of these factors. There's a lot of simplification that could happen here, but that's not what we're worried about right now. We're just worried about taking the derivative. Okay, here I've got x raised to a power of x. Anytime you've got an x being raised to a power of x, or more importantly, anytime you've got an x up here in the exponent, you're probably going to have to use logarithmic differentiation. So we take the natural log of both sides. Then we take the derivative. The whole reason we take logs of both sides is to get this exponent to come down. So let's do that first. This exponent will come out front. Remember, that's natural log of 3x plus 1. That's not times. There's a times here. This is 2x times that stuff. Now we take the derivative of both sides. Oh. So that guy's derivative and this product's derivative. The derivative of natural log of anything is 1 over that thing times the derivative of that thing. The derivative of y is y prime. Over on this side, I have to use product rule. I've got a product. Here's one function. Here's another. And when I get to that guy, I'm going to have to use chain rule. The derivative of 2x is 2 times leave the second alone, plus derivative of the first one, derivative of the second, the derivative of natural log of anything is 1 over that thing times the derivative of what was inside. So derivative of 3x plus 1 would be 3 times the second. So derivative of the first times the second plus derivative of the second times the first. Now I'm trying to solve for y prime, so I need to multiply the y over. Y prime will be y times all of this stuff. But I know what y is. It's the original. It's this. So we get y prime equals natural log 3x plus 1 raised to the 2x times 2 ln of 3x plus 1 plus, and I'm going to go ahead and combine those together. That's 6x over 3x plus 1. And I need that bracket there. Here's my derivative. And the only way we could have gotten here is logarithmic differentiation. We're going to need that on this too. Anytime you've got your independent variable up in an exponent, you're probably going to need logarithmic differentiation. So let's call this guy y. This is sine of t raised to the e to the t power. So I take the natural log of both sides. And I'm taking log of that. Then the whole point of taking logs is this guy in front can come down, or this guy in the exponent can come down front. Now I take the derivative of both sides. Over here, I'm going to have to use chain rule because y is a function of t. This is implicit differentiation we're doing here. Over here, I'm going to have to use product rule because I have two functions, function number 1, function number 2. And I'm going to have to use chain rule because this is a function inside a function. So we're kind of planning ahead. The derivative of natural log of anything is 1 over that thing times the derivative of what's inside. So derivative of y is y prime. That's what we're trying to find. Over here, I've got a product. Derivative of e to the t is just e to the t times, leave the second one alone, plus. Now derivative of the second. The derivative, I'm so sick of saying the word derivative, but I'm going to say it a lot. Derivative of natural log of anything is 1 over that thing times the derivative of whatever's inside. Derivative of sine of t is cosine of t times, leave the first alone. Derivative of the first times the second plus derivative of the second times the first. Now in trying to get y prime by itself, so I multiply that y over, so I get y times all this stuff. All that's going to come down. And I know what y is. That's the original. So y prime will be sine of t raised to the e raised to the t times, and a whole bunch of parentheses here, or at least one set of parentheses. All that stuff up here. Now I would go ahead, I got cosine over sine. I would write that as cotangent of t. So that's cotangent of t times e to the t. Okay. I've got a chain rule. I've got a function inside a function. So y prime, also known as dy dx. My independent variable is x here. The derivative of arctan of anything. So arctan of, say, u, derivative will be 1 over 1 plus u squared times the derivative of whatever's inside, the derivative of u with respect to your independent variable. That's a plus right there. So derivative of arctangent, 1 over 1 plus whatever's inside in parentheses squared times the derivative of what was inside. This is what's playing the role of what I called u. So I want his derivative with respect to x here, and I'm going to need parentheses. Derivative of x with respect to x is 1, and the derivative of sine of x is cosine of x. So there's my derivative. Can that clean up? I don't know, maybe. I don't see any way immediately to clean it up. Okay. We got an arcsine. Now, you may not remember the derivative of arcsine. That might be one you have to look up. So, like on a test, I would give you this one. I don't expect you to remember that derivative, but I'll write it over here. The derivative of arcsine or inverse sine of some function u is 1 over the square root of 1 minus u squared times the derivative of whatever was inside, if x is our independent variable here. So y prime here will be derivative of arcsine of junk is 1 over square root of 1 minus junk squared times derivative of what's inside. Now we got to remember, this was prime. The derivative of a to the x is a to the x times natural log of a. That one you do need to remember. When a equals e, natural log of e is 1. That's why the derivative of e to the x is just e to the x. I mean, I could put a natural log of e here, but that's just 1. So I want derivative of 2 to the x, that's 2 to the x times natural log of 2. And this is not going to clean up at all. Okay, I've got a chain rule here. I've got a function inside another function. So I'm going to have to chain rule that. I would first think of this as y equals all this junk to the 1/2 power, and then use power rule. Plus there. So I'm going to have to do some chain ruling here. The derivative of junk to the 1/2 power is 1/2 times junk to the negative 1/2 power. So the power comes down, leave the inside alone, and then drop the power down by 1. 1/2 minus 1 is negative 1/2 times the derivative of what's inside. So this is chain rule. Now, what's inside is a fraction, so I'm going to have to use quotient rule here. Derivative of the top is 3. Leave the bottom alone. Plus derivative of the bottom. And I need parentheses here. A lot of times people leave off all these parentheses. That's going to be 7x to the 6th plus the derivative of 4 to the x. That's this problem again, right here. The derivative of 4 to the x is 4 to the x times natural log of 4 times the top. Oh, and sorry, that I got to fix that. That's a minus. Let me fix this. So derivative of the top, leave the bottom alone, minus derivative of the bottom times leave the top alone, all over the bottom squared. Now, could this be cleaned up? Yeah, absolutely. There's a lot of algebra that could be done to clean this up, but I think it's perfect the way it is. Okay, now we've got this one, and we could do this as chain rule. Or sorry, we could do this as quotient rule because we've got a fraction. But I think it's much easier to think of this guy because we just got a constant on top. Derivative of a constant is 0 anyways. Let's rewrite this guy as 2 times 4x to the 5th plus pi to the negative 8th power, and then just use chain rule instead of quotient rule. We're going to need chain rule anyways. This is going to be much easier. So y prime will be, I've got the 2 is going to come along for a ride. I've got junk raised to a power. The power is going to come down and multiply. Negative 16. Leave the inside alone. And then the power will drop down by 1. So negative 8 minus 1 is negative 9. Times the derivative of what's inside. Derivative of 4x to the 5th is 20. X to the 4th, and then here students get confused. Pi is just a number. The derivative of any constant is 0. I mean, I could put plus 0 here if I want, but then it's just cluttering it up. It's not necessary. We're done. That's it. Okay, that's a good place to stop on this one.